Something is wrong with the universe. Not wrong in the way that scientists sometimes use that word. Not a minor anomaly at the edge of a data set. Not a rounding error in a theoretical prediction. Not a tension that might go away with better calibration. Wrong in the deepest, most foundational sense. Wrong in the sense that the universe is doing something that no version of physics, before about 1998, predicted it would do. The universe is tearing itself apart. Slowly, right now, in the space between every galaxy and every galaxy cluster, in the vast, dark, apparently empty voids that make up most of the volume of the cosmos, something is pushing. Not gravity. Gravity pulls. This something pushes. It works against every attractive force that has ever been measured or theorized. It drives the fabric of space itself to expand faster and faster, year on year, decade on decade, carrying the galaxies apart at increasing speed. And we have no idea what it is. We have a name for it. We call it dark energy. We know roughly how much of it there is. It makes up approximately 68% of the total energy content of the universe. We know what it does. It drives the accelerating expansion that was discovered in 1998 and has been confirmed by every subsequent measurement with increasing precision. We know with extraordinary accuracy its current effect on the geometry and dynamics of the cosmos. What we do not know is what it actually is, where it comes from, whether it will remain constant, whether it might change, whether it might, over the next tens of billions of years, grow stronger. And here is why that last question matters more than almost anything else in modern physics. If dark energy is constant, if the pushing force stays at its current level, the future of the universe is one of increasing loneliness. Galaxies drift apart, stars burn out, the universe cools and darkens and eventually settles into a frozen, featureless equilibrium. A long, cold death, but a death in which everything that forms remains intact until it exhausts its own energy. But if dark energy is not constant, if the pushing grows, the future is very different, more violent, more sudden, more complete. In one of the most serious cosmological models currently entertained by physicists, dark energy could grow strong enough to eventually overcome not just the expansion of the universe, but gravity itself, and then the electromagnetic force, and then the nuclear forces. In this scenario, which has a name, and which we will get to, every structure in the universe is destroyed. Not just galaxies and stars, planets, molecules, atoms, atomic nuclei. In the final moments, even the protons and neutrons themselves are ripped apart by the expansion of space. The universe ends, not with a whimper, not with a freeze, but with a total, violent, absolute destruction of everything that exists. The current best estimates put this event, if it happens, approximately 22 billion years from now. This is the story of what is happening right now to the universe at the largest scales. It is the story of a discovery that shook cosmology to its foundations, of a constant that Einstein invented and then abandoned that turned out to be real after all, of a tension between two measurements that should agree and conspicuously do not, and of the end of everything, if the numbers are pointing where some physicists fear they might be pointing. Let's start at the beginning, or rather, let's start at the end. Chapter 1. The night the universe stopped making sense. In 1998, two teams of astronomers were doing something very specific and very painstaking. They were hunting exploding stars in distant galaxies. Not for the spectacle, not for the light show. They were hunting them because exploding stars of a specific type, a type called Type 1a supernovae, are, in a very precise sense, all the same brightness. Not exactly the same, but close enough and measurably correctable that they can be used as what astronomers call standard candles. Objects of known intrinsic luminosity that, when you observe them, let you calculate how far away they are simply by measuring how bright they appear. The further away, the dimmer. Measure the apparent brightness, compare to the known intrinsic brightness, do the inverse square law calculation, and you have a distance. In the universe, distance to a distant galaxy is tightly connected to how fast it's moving away from us. The Hubble law. The further a galaxy is, the faster it recedes, because there is more space between us and it, and all that space is expanding. So if you can measure distances to a large sample of distant galaxies, you can map the expansion history of the universe, how fast it was expanding at different epochs in cosmic history. That was the goal. The two teams, the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter, were both trying to measure the deceleration of the universe. Not the acceleration, the deceleration. Everyone knew the universe was expanding. Hubble had established that in 1929. The question was how quickly the expansion was slowing down. Gravity pulls everything toward everything else. In an expanding universe, gravity should be acting as a brake, gradually slowing the outward rush of galaxies. The question was just how strong the brake was, how much matter there was to generate how much gravitational pull, and therefore how quickly the expansion would eventually stop and possibly reverse into a big crunch. They expected to measure a number less than 1, a number representing gentle deceleration. Maybe the universe was dense enough to eventually recollapse. Maybe it would expand forever, but increasingly slowly. Either way, the answer would tell them about the ultimate fate of the cosmos. They did not get a number less than 1. The Wuhan distant supernova were dim, too dim. Not dramatically, not obviously, immediately, slam you in the face dim, but systematically, persistently, undeniably dim. When the teams compared the apparent brightness of their high redshift supernovae to what they expected, based on the distance implied by the supernovae's redshifts, assuming a decelerating universe, the supernovae were further away than they should have been. The universe was not decelerating, it was accelerating. The expansion of the universe was not slowing down under the influence of gravity, it was speeding up. The distant galaxies were receding faster than they should have been. The universe was not braking. Something was pressing the accelerator. When Adam Rees processed the data from the High Z team and saw what it implied, his first response was to assume he had made a mistake. He went through the analysis again and again. He looked for systematic errors, dust in the intergalactic medium that might be, absorbing light and making the supernovae look fainter. He looked for evolution, the possibility that Type 1a supernova in the early universe were intrinsically different from nearby ones, throwing off the standard candle calibration. He found no errors. He found no convincing systematics. The data said what the data said. He called Schmidt, the team leader. Schmidt ran through the analysis himself. He got the same answer, He called it, in a later interview, the most disappointing result I could imagine. He had hoped to measure the deceleration. Instead, he had found something that, by the physics of the time, should not exist. Perlmutter's team found the same thing, independently. 2 teams, using different subsets of supernovae, different analysis pipelines, different telescopes, the same result. The fact that it was 2 independent teams is the critical detail. Science is full of surprising individual results that later turn out to be wrong. A statistical fluctuation, and high, unnoticed systematic, a subtle error in the analysis. What makes a result credible is independent confirmation. When 2 teams set out to measure the same thing, using different data and different methods, and arrive at the same unexpected answer, the probability that both are wrong in exactly the same way drops precipitously. The High Z team and the Supernova Cosmology Project were not collaborators. They were competitors, racing to publish, watching each other's preprints with the particular attention that competitive scientists pay to the work of people trying to beat them to the same discovery. They had different approaches to selecting their supernovae, different strategies for observing them, different teams of graduate students running the numbers. They were not set up to agree. They had every reason to want their own answer to be correct, and the other teams to be slightly different. They agreed anyway, not on a value anyone expected, but on a value nobody had predicted. Ries later described the moment he understood what his data was telling him. He had been running what he called a sanity check, applying his calibration pipeline to a different subset of nearby supernovae to make sure the method was working correctly. It worked. The nearby supernovae gave the expected answer. Then he ran it on the distant sample, and the number came back wrong. Not slightly wrong. Consistently, systematically wrong, in a direction that pointed at only one explanation. He sat with the result for 2 weeks before telling anyone. He kept looking for the error. He varied the statistical methods. He removed individual outlier supernovae and checked whether the result held. It held. Whatever was causing the distant supernovae to look too dim was not a handful of anomalous objects. It was the whole population. When he finally presented the results at a conference in December 1997, several months before the formal announcement, the reaction in the room was by multiple accounts, stunned silence followed by intense questioning. Not hostile questioning, not the reaction to a result people think is wrong. The reaction to a result people can't immediately find fault with, but can't quite bring themselves to believe. The universe was accelerating. Something was pushing it, and no one had the faintest idea what. In 1998, the results were announced. The universe's expansion is accelerating. Something is pushing the cosmos apart, working against gravity on the largest scales, and getting stronger as the universe expands. The announcement made the front pages of every major newspaper. Science magazine named it the breakthrough of the year. In 2011, Schmidt, Ries, and Perlmutter shared the Nobel Prize in Physics for the discovery. And physicists all over the world started asking the same question with varying degrees of panic in their voices. What is doing the pushing? Chapter 2, Einstein's greatest blunder, was not a blunder. To understand dark energy, you have to go back to 1917. to a letter that Albert Einstein sent to colleagues containing a mathematical term he had added to his field equations, a term that would haunt the history of physics for the next century. Einstein had just finished his general theory of relativity, published in 1915. The theory was beautiful. It described gravity not as a force, but as the curvature of space-time caused by mass and energy. It made predictions, the bending of light around massive objects, the precession of Mercury's orbit, the gravitational redshift of light, that Newtonian gravity could not match. It was, by any measure, one of the greatest intellectual achievements in human history. But when Einstein applied his new equations to the universe as a whole, he found a problem. The equations predicted a dynamic universe. A universe that was either expanding or contracting, but not static. Einstein, in 1917, believed the universe was eternal and unchanging, the prevailing view of the time. A universe that was either growing or shrinking didn't fit the philosophy, so he added a term, the cosmological constant, written as the Greek letter lambda. It was a term that represented a kind of repulsive energy built into the fabric of space itself, an energy that pushed outward, balancing the inward pull of gravity, holding the universe in a static, steady state. With the right value of the cosmological constant, gravity and the lambda term canceled exactly, and the universe neither expanded nor contracted. Einstein was satisfied. The equations produced a static universe. The universe was, as far as anyone could tell, static. Problem solved. Then, in 1929, Edwin Hubble published his observations showing that distant galaxies were moving away from us, and the further away they were, the faster they were receding. The universe was not static, it was expanding. It had been expanding all along. There was no need for the cosmological constant to hold it in balance. The balance Einstein had been looking for was not the right question. Einstein removed the cosmological constant from his equations. He reportedly called it his greatest blunder, the introduction of an artificial term to avoid a prediction his equations were making correctly, a prediction he didn't believe because it contradicted his philosophical priors. For decades, the cosmological constant sat in the dustbin of physics history, a well-intentioned mistake by a great physicist, a reminder that even geniuses can fool themselves. Then 1998 happened. The accelerating expansion discovered by the supernova teams was not just surprising. It was mathematically precisely what a positive cosmological constant would produce. Einstein's term, the one he invented to hold the universe still, the one he later called a blunder, reinserted into the equations with the right value, perfectly described the observed acceleration. Not approximately, precisely. Einstein's greatest blunder turned out not to be the introduction of the cosmological constant. It was the removal of it. In modern cosmology, the cosmological constant is the leading candidate for dark energy. It represents the energy density of empty space, the vacuum energy. The idea is that the quantum vacuum, even in regions completely empty of particles, is not truly empty. Quantum mechanics requires that even in vacuum, virtual particles are constantly popping in and out of existence. Quantum fluctuations of every possible field, at every possible energy, frothing ceaselessly in what appears to be empty space. These fluctuations have energy. And energy, according to general relativity, gravitates. It has a gravitational effect on the curvature of space-time. The vacuum energy of quantum fields, the theory goes, is the cosmological constant. It is the energy of empty space. It is the pushing force. It is dark energy. This is an elegant answer. It connects the observed phenomenon, accelerating, expansion, to a well-established physical principle, quantum vacuum fluctuations. It requires no new physics. It requires only taking quantum mechanics seriously in a cosmological context. Except there is a problem, the single largest problem in all of theoretical physics. When you actually calculate the vacuum energy using quantum field theory, when you sum up the contributions of quantum fluctuations from all the known fields at all the energies where they operate, you get a number. And the number you get is not the number you need. It is off by 120 orders of magnitude. Let me try to convey what that means. An order of magnitude is a factor of 10. 10 orders of magnitude is a factor of 10 billion. 120 orders of magnitude is a factor of 10 raised to the power of 120. Written out, that's a 1 followed by 120 zeros. The theoretical prediction for the vacuum energy density based on quantum field theory is 10 to the 120 times, larger than the value we actually measure from the accelerating expansion of the universe. If the theoretical prediction were correct, the cosmological constant would be so enormous that the universe would have expanded explosively in its very first moments, far too fast for any structure, galaxies, stars, planets, atoms, to ever form. There would be no universe as we know it. There would, in any meaningful sense, be nothing. This discrepancy between the quantum field theory prediction and the observed value is called the cosmological constant problem. It has been described as the worst prediction in the history of science. The largest discrepancy between theory and observation ever recorded. A numerical mismatch so enormous that it cannot be a coincidence or a small systematic error. It requires that something, some physical principle we do not yet understand, is suppressing the vacuum energy by a factor of 10 to the 120 from what the naive calculation gives. Nobody knows what that something is. This is the deep mystery at the heart of dark energy. We know its effect. We know its approximate magnitude. We have a name, the cosmological constant, that describes it mathematically. But we do not know why it has the value it has, why it isn't 10 to the 120 times larger, or what physical principle sets its value. It is, in the most literal sense, one of the great unsolved problems in all of science. Chapter 3, Two Numbers That Don't Agree, and Why That's Terrifying. Here is where the story of dark energy gets stranger, because in recent years, a new problem has emerged, one that is, in some ways, even more alarming than the cosmological constant problem. Two independent ways of measuring how fast the universe is currently expanding give different answers, not slightly different, not within each other's error bars, in a way that might be explained by statistical fluctuation, consistently, persistently, stubbornly, significantly different. The measurement of the expansion rate is called the Hubble constant, written as h0. It tells you, in kilometers per second, how fast a galaxy is receding for every megaparsec of distance between you and it. It is the fundamental parameter of cosmological expansion, the number that sets the scale of the universe, determines its age, and governs how everything in it evolves over time. For decades, measuring the Hubble constant precisely was one of the great goals of observational cosmology. The answer matters enormously for determining the age of the universe, for predicting its future, for testing our models of its contents and history. It was also extremely hard to measure because every measurement requires a chain of distance calibrations, the distance ladder, each step of which introduces its own uncertainties. By the early 2000s, after enormous effort, the Hubble constant was pinned down to within about 10%. By the 2000s, measurements were claiming precision at the few percent level, and they disagreed. The first method is the early universe approach. You take the cosmic microwave background, the most precisely measured object in all of cosmology, mapped to extraordinary resolution by the Planck satellite, and you fit the standard cosmological model to it. The CMB data alone, combined with a small amount of additional information about large-scale structure, determines the cosmological parameters, including the Hubble constant, to remarkable precision. The Planck team's analysis gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method is the late universe approach. You build the distance ladder from the ground up. You use Cepheid variable stars, stars that pulsate with a period directly related to their intrinsic luminosity, to calibrate distances to nearby galaxies. You use those calibrated galaxies to calibrate the brightness of type 1a supernovae in them. You then use the supernovae, the same kind used to discover the acceleration in 1998, as standard candles to measure distances across billions of light years. At each step, you measure apparent brightness, apply your calibration, and extract a distance. Build enough of the ladder and you get to galaxies far enough away that their recession velocity is large compared to local motions. And from that recession velocity, you can read off the Hubble constant directly. Multiple teams using this method, using different calibrators and different supernovae samples and different statistical approaches, consistently get approximately 73 kilometers per second per megaparsec. 67.4 versus 73. That's an 8% discrepancy. At the precision, these measurements are now claiming, a few percent or less, this is a discrepancy of more than 5 standard deviations. In particle physics, 5 sigma is the threshold for a discovery. In cosmology, it means the two measurements are statistically incompatible. They cannot both be right if the standard model is correct. This is called the Hubble tension. It is currently the most significant unexplained discrepancy in observational cosmology. And it has been getting worse, not better, as both measurements have become more precise. Every refinement of the CMB analysis, every additional supernova, every improved Cepheid calibration has sharpened the discrepancy rather than resolving it. The standard response to attention in science is to look for systematic errors. Maybe the Cepheid calibration has a subtle error that inflates the distance ladder value. Maybe the Planck CMB analysis has a systematic that pulls the early universe value low. Enormous effort has gone into investigating both possibilities. The Hubble Space Telescope's SHOES program spent years refining the Cepheid calibration. The James Webb Space Telescope has now provided independent checks using a different method. JWST measured Cepheid distances to the same calibrator galaxies and got results consistent with Hubble, suggesting the Cepheid calibration is not the problem. Alternative distance indicators have been pressed into service. The tip of the red giant branch, a different kind of standard candle based on the brightness at which old red giant stars suddenly start helium burning, gives a Hubble constant that sits between the two discrepant values, closer to 70. Surface brightness fluctuations in early-type galaxies give another measurement. Megamaser distances give another. The gravitational wave standard siren method, using neutron star mergers as absolute distance indicators, gives a value broadly consistent with 70, with uncertainties still too large to definitively resolve the tension. None of them has resolved it, which means the other possibility has to be taken seriously. Maybe there are no systematic errors. Maybe both measurements are correct, and the tension is real. Maybe the standard cosmological model, lambda CDM, the model underpinning both analyses, is missing something. Maybe the universe between the epoch of the CMB and the present day has evolved differently from what the standard model predicts. Maybe something changed in the expansion history, a brief episode of additional energy, a modification to gravity, a change in dark energy that drove the universe to expand faster than lambda CDM expects. If that's the case, if the Hubble tension is not a systematic error, but a real discrepancy, then the standard model is wrong in a way we don't yet understand. Dark energy may not be constant. The cosmological constant may be an approximation rather than the true description. The universe may be more dynamic, more complicated, more surprising than even the post-1998 picture suggests. In 2024, data from the Dark Energy Spectroscopic Instrument, DESI, added a new layer to this story. DESI is a ground-based spectrograph capable of measuring the redshifts of millions of galaxies simultaneously, mapping the three-dimensional distribution of matter across billions of light-years. In its first major data release, the DESI team reported results that, when combined with other datasets, showed tentative evidence that dark energy may not be constant. The data preferred, at roughly 2 to 3 sigma, a model in which dark energy changes over time, a so-called dynamical dark energy, rather than the fixed cosmological constant of lambda CDM. The specific model DESI's data seemed to favor is called W0WACDM, a two-parameter extension of lambda CDM, in which the dark energy equation of state is not fixed at -1, but varies as a function of cosmic time. The parameter WU0 describes dark energy today. WA describes how it evolves with time. DSI's best fit put W0 somewhat above -1, suggesting dark energy is slightly weaker today than a cosmological constant. But WW, a strongly negative, suggesting dark energy was stronger in the Taiyup past and is weakening. The combined picture, dark energy that has been declining, having been more powerful in the early universe than it is now. If true, this is profoundly important. It would mean dark energy is not the cosmological constant, but a dynamic field, evolving over cosmic time. It would mean the future acceleration of the universe might be less severe than lambda CDM predicts. Or, depending on the trajectory of the field, potentially more severe. It would mean that the simple, elegant picture of a fixed vacuum energy pervading all of space is wrong, and something more complicated is operating. But the DeSci team were careful to emphasize the limitations of their result. 2-3 sigma is not a discovery. It is a hint, a result that needs to be confirmed with more data, more survey volume, better systematic control, and independent confirmation from other instruments. The full DeSci survey is still ongoing. The 2024 data release covered 1 year of operations out of a planned 5-year program. By the time DeSci completes its survey, it will have mapped tens of millions of galaxies, and the statistical power will be several times greater. If the hint of dynamical dark energy is real, the full dataset should reveal it clearly. If it reveals the opposite, if the full DESI dataset converges on W equals -1, with the early hint dissolving into statistical noise, that too will be important. It will tighten the constraints on the cosmological constant, pushing the equation of state ever closer to -1, and making phantom energy progressively less likely. Either way, DSI is going to tell us something new about dark energy. Either it will confirm that dark energy is dynamical, opening a new era of dark energy physics, or it will confirm that it is constant, deepening the mystery of why the vacuum energy has exactly the value it does. 2-3 sigma is not a discovery. It is, though, the most interesting 2-3 sigma in modern cosmology. And it is why the question of what dark energy is and what it will do is not a question for the distant future. It is a question being actively answered right now by instruments operating right now, with data coming in right now. Which means the unusual thing happening to the universe is not just a background fact. It is an active investigation, a live mystery. And we are watching it in real time. Chapter 4, the fabric of space is stretching. Right now, under your feet. Before we get to the far future, let's make sure we understand what the accelerating expansion actually means. Not in the abstract, in the immediate, physical, right now sense. The universe is expanding. Space itself is stretching. The fabric of space-time, the four-dimensional medium through which all things move, the stage on which all physical processes play out, is growing in every direction, continuously, at every moment, including right now as you watch this. This is not metaphor. It is not analogy. It is the literal content of the best confirmed theory of gravitation ever devised. General relativity applied to a homogeneous isotropic universe filled with the observed mix of matter, radiation, and dark energy gives equations whose solution is an expanding spacetime. The expansion is not the motion of galaxies through space, the way an explosion sends shrapnel flying through the air. It is the growth of space itself, carrying the galaxies along with it the way raisins in a rising loaf of bread are carried apart by the expanding dough. In a rising loaf, the raisins themselves don't move through the dough. The dough between them grows. The distance between raisins increases, not because the raisins moved, but because the medium they're embedded in expanded. Two raisins near each other get further apart slowly. Two raisins far apart get further apart faster because there's more dough between them to expand. Measure the recession speed of a distant raisin and it's proportional to its distance. Exactly the Hubble law. Now, this expansion is happening everywhere, including right here, including in the room you're sitting in, including between you and the screen you're watching on. including between the atoms in your body. Why then does the room not expand? Why do you not feel stretched? Why are the planets not drifting away from the sun, the Milky Way not coming apart at the seams? Because expansion is opposed by forces, and on small scales, the scale of rooms, planets, solar systems, galaxies, those forces win. Gravity, electromagnetism, the nuclear forces. All of these bind matter together. A hydrogen atom doesn't fly apart under cosmic expansion because the electromagnetic attraction between its proton and electron is overwhelmingly stronger than the cosmological expansion's tendency to pull them apart. The Earth doesn't drift away from the sun because the sun's gravity is enormously stronger than the expansion's pushing. The Milky Way doesn't dissolve because the gravitational binding of hundreds of billions of stars and dark matter keeps the whole structure intact. And here is something that almost nobody mentions when explaining cosmic expansion, but which changes how you intuitively understand what's happening. The expansion of the universe does not act like a wind, pushing on objects, trying to move them apart, resisted by forces. It acts more like the absence of a force that would otherwise be pulling things together. On cosmological scales, gravity is insufficient to hold things together, so they separate. On local scales, gravity and electromagnetism are sufficient, so things don't separate. The expansion doesn't fight gravity and lose on local scales. Gravity wins locally by being so much stronger that the expansion's contribution is entirely negligible. To get a sense of the numbers, the cosmological acceleration corresponding to the current value of dark energy is, on the scale of a meter, roughly 10 to the minus 35 meters per second squared. That is so small as to be meaningless compared to any other force in daily experience. It would take trillions of years for that acceleration to produce a perceptible effect over a 1 meter distance, and every other force would overwhelm it long before it mattered. The expansion only wins where gravity doesn't. In the vast spaces between galaxy clusters, the cosmic voids, the enormous empty regions that make up most of the universe's volume, there is nothing to oppose the expansion. No gravity strong enough to matter. No electromagnetic force to bind anything. Just the fabric of space stretching, carrying nothing with it, growing year on year, accelerating, pushing the galaxy clusters apart at increasing speed. Right now, the Virgo cluster, the nearest large cluster of galaxies to our own local group, is receding from us at about 1,100 kilometers per second. It's about 65 million light years away. The Coma cluster, 330 million light years away, recedes at about 7,000 kilometers per second. These are not absolute speeds. There are local motions superimposed, but they give the scale. Cosmological expansion is a process operating at thousands of kilometers per second across hundreds of millions of light years. And it is accelerating. The recession speed of a galaxy at a given distance is not constant over time. It increases. A galaxy cluster that is currently receding at 1,000 kilometers per second will, in several billion years, be receding at a higher rate, because the expansion has accelerated in the intervening time, driven by dark energy. The space between us and it has grown, and dark energy's effect grows proportionally with the volume of space. There is a specific distance, called the Hubble radius or the Hubble horizon, at which the recession speed equals the speed of light. At that distance, the space between us and a galaxy is expanding at exactly 300,000 kilometers per second. Anything beyond that distance is receding from us faster than light. This does not violate special relativity. Special relativity limits the speed of objects moving through space. The galaxies beyond the Hubble horizon are not moving through space faster than light. The space itself is expanding, carrying them away from us at faster than light recession speeds. There is no physical speed limit on how fast space can expand, but there is a consequence. Galaxies beyond a certain distance, the cosmological event horizon, are permanently, irrevocably beyond our reach. Not just currently beyond our reach forever. Any signal we send today, even a light beam, the fastest thing there is, will never reach them because the expansion is carrying them away faster than the signal can cross the gap. And because the expansion is accelerating, the event horizon is actually shrinking over time. More and more galaxies are being cut off from our future light cone. The galaxies we can currently see, the 2 trillion or so galaxies in the observable universe, are not all galaxies we can communicate with. And the number we can communicate with is decreasing year by year, as the accelerating expansion carries more of them beyond the event horizon. In roughly 2 billion years, the Virgo supercluster, the large-scale structure that contains our local group, will begin to dissolve as expansion overcomes the weak gravitational bonds holding its outer regions together. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way, a merger that has nothing to do with expansion being driven by local gravity. But the merged galaxy, Milkomeda, will increasingly find itself in a universe growing emptier around it. In roughly 100 billion years, all galaxies outside our local group will have receded beyond the event horizon. Milkomeda will sit alone in a dark, empty, expanding void with no observable evidence that any other galaxy has ever existed. And this is the good scenario. This is the future if dark energy is constant. If the cosmological constant is the right description, if the universe simply continues its current trajectory indefinitely. If dark energy is something else, something that grows, the future is worse, considerably worse. Chapter 5: What phantom energy is and why some physicists are genuinely afraid of it. In 2003, a physicist named Robert Caldwell at Dartmouth College published a paper with one of the more memorable titles in the history of cosmological literature. The paper was called Phantom Energy, Dark Energy with W less than -1 and the Big Rip Scenario. It described the end of the universe. To understand why, you need to know about a number called the equation of state parameter, written as W. It describes the relationship between the pressure of a substance and its energy density. For ordinary matter, W is approximately 0. Matter has energy density but negligible pressure on cosmological scales. For radiation, W is 1/3. For the cosmological constant, the simplest form of dark energy, W is exactly -1. That -1 is the critical value. It means the energy density of dark energy stays constant as the universe expands. As space grows, the total dark energy in the universe increases. More space means more vacuum energy. But the energy density per unit volume stays the same. Lambda is constant. That is what the cosmological constant means. But there is no fundamental physical principle, that requires a W to equal exactly -1. It could be minus 0.9. It could be minus 1.1. The observational measurements are consistent with -1, but do not, at current precision, rule out values on either side. And the sign of W plus 1, whether W is greater or less than -1, makes an enormous difference. If W is greater than -1, if W equals minus 0.9, say, then dark energy weakens over time as the universe expands. This is called quintessence. The dark energy is not a fixed constant, but a dynamic field that dilutes slowly, less quickly than matter or radiation, but still decreasing. In this scenario, the expansion eventually slows, not necessarily reversing, but not accelerating as violently as today. The future is a slow fade. If W equals exactly -1, you have the cosmological constant energy density, steady acceleration, lonely but not violent future. If W is less than -1, if W equals -1.1, -1.3, -2, you have what Caldwell called phantom energy, dark energy that grows stronger as the universe expands. Not just constant energy density, but increasing energy density. Dark energy that becomes more and more powerful the larger the universe gets. A universe with phantom energy is a universe with a runaway accelerator that never hits a limit. And in a universe with phantom energy, the expansion does not just accelerate gently and indefinitely. It accelerates, and then accelerates its acceleration, and then accelerates that, in a positive feedback loop that grows without bound, heading toward a singularity in finite time. That singularity is called the Big Rip. Caldwell and his collaborators calculated what a big rip would look like. What would happen in the final moments and the final epochs of a universe with phantom dark energy? The answer is a systematic, ordered destruction of every bound structure in the universe, working from the largest scales down to the smallest, with a ruthless precision driven purely by the mathematics of exponential expansion. The timeline for a dark energy equation of state of W equals -1.5 and the current observational constraints puts the Big Rip approximately 22 billion years from now, long enough that no civilization existing today needs to worry about it in any practical sense. Short enough, just over 1.5 times the current age of the universe, to be a genuinely near-term cosmological event on the scale of cosmic history. Here is how it plays out. 2 billion years before the Big Rip, the local supercluster begins to dissolve. The weak gravitational threads holding together the sprawling structure that includes our local group, the Virgo cluster, and dozens of other galaxy groups are overcome by the phantom expansion. Galaxies that have been gravitationally associated for billions of years begin to separate, carried apart by space itself. 1 billion years before the Rip, individual galaxy clusters break apart. The Virgo cluster, 1,300 galaxies bound together by the gravity of their combined mass and dark matter halos, is torn asunder. The galaxies that have orbited within it for billions of years separate, carried into the expanding void, each alone. 60 million years before the Rip, the Milky Way itself begins to dissolve. The gravity of our own galaxy, the gravitational binding of 400 billion stars, spanning 100,000 light years, is not strong enough to hold against the phantom expansion. Stars at the outer edges of the galaxy begin to be stripped away. The spiral arms fray. The disk begins to disperse. 3 months before the rip, the solar system comes apart. The sun's gravity, which has held the planets in their orbits for 4.6 billion years, is overwhelmed by the expansion. The planets spiral outward, one by one, receding from the sun and from each other. Earth drifts away from the sun. The familiar sky, with its sun and moon and planets, changes beyond recognition in the final months before the end. 30 minutes before the rip, the Earth itself is ripped apart. Not by any external force, not by impact or explosion, but by the expansion of space within the Earth's own structure. The electromagnetic forces binding rock to rock, molecule to molecule, are overcome. The planet disintegrates. In the final fraction of a second, atoms are pulled apart. The electron orbits in hydrogen and oxygen and carbon. The atoms that make up every living thing, every rock, every drop of water, are disrupted. The electrons are dragged away from their nuclei. And in the very last instance, the strong nuclear force, the force that has held protons and neutrons together since the universe was 3 minutes old, is overcome. Atomic nuclei split apart. Protons and neutrons are torn from each other. And then space-time itself reaches a singularity. The expansion rate becomes infinite. The universe ends, not with a whimper, not with a freeze, with the complete, absolute, total annihilation of every particle and structure that has ever existed. Now, is this going to happen? The honest answer is that we don't know. Current measurements of the dark energy equation of state are consistent with W equals -1, the cosmological constant. The DC data from 2024 showed hints that W might be evolving, but at only 2 to 3 sigma, not a definitive result. The Hubble tension may or may not be evidence of non-standard dark energy behavior. The data right now does not require phantom energy, but the data does not rule it out, and the consequences of it being true are significant enough that the possibility deserves to be taken seriously. The reason physicists take it seriously is not because the evidence is strong. It is because we don't know what dark energy is. We have no theory that predicts W equals -1 from first principles. We have no physical argument for why dark energy should be exactly a cosmological constant rather than a dynamical field. Given our profound ignorance about what dark energy actually is, the question of whether W is exactly -1, slightly above it or slightly below it, is an open empirical question, one that only better measurements can answer. And better measurements are coming, not eventually, soon. Multiple experiments, operating right now or completing their builds as you watch this, are designed explicitly to nail down the dark energy equation of state with precision that will either confirm the cosmological constant or break it. Understanding what those instruments are, what they can measure, and what they've already found is how we get from maybe the universe is going to rip apart to here is what the data actually shows. That is where we are going next. Chapter 6. The instruments racing to measure. Dark energy. The question of what dark energy is, whether it is constant, whether it is growing, whether the universe is heading for a quiet freeze or a violent rip, is not going to be answered by theory alone. Theory has been trying for 25 years and has produced no consensus, no candidate particle, no physical mechanism with more than circumstantial support. The answer, when it comes, will come from measurement, from instruments pointed at the sky, accumulating data, narrowing the constraints on W until the uncertainty is small enough to distinguish a cosmological constant from phantom energy. That project is underway right now, and the instruments involved are, in their own way, as remarkable as the phenomenon they're investigating. Start with DESI, the Dark Energy Spectroscopic Instrument, which we met in the last chapter. DESI sits at the prime focus of the Mayal telescope at Kitt Peak National Observatory in Arizona, 4,000 feet above the Sonoran Desert. Its primary instrument is a fiber optic spectrograph connected to 5,000 robotic fiber positioners, small, individually addressable robots, each the diameter of a pencil, packed into a focal plane the size of a dining table. Each robot can move its fiber to point at any target within a small patrol radius, and in the roughly 10 minutes it takes to observe one field, all 5,000 fibers are simultaneously measuring the spectrum of 5,000 different objects, galaxies, quasars, stars, spread across a patch of sky. A spectrum gives you a redshift. A redshift gives you a distance. A distance, combined with the galaxy's position on the sky, gives you its three-dimensional position in the universe. Do this for millions of galaxies, spread across billions of light years, and you build a map, a three-dimensional map of the cosmic web, showing where the galaxies cluster and where the voids yawn between them. That map contains dark energy information in a subtle but powerful way. In the early universe, about 380,000 years after the Big Bang, when the CMB was released, a specific physical process left a characteristic scale imprinted in the distribution of matter. Before the CMB was released, the universe was a hot plasma of photons and baryonic matter, and the pressure waves propagating through that plasma, acoustic oscillations driven by the competition between gravity and radiation pressure, established a preferred length scale. When the universe became transparent and the plasma froze, that preferred scale was locked into the distribution of matter. Galaxies are slightly more likely to be separated by about 500 million light-years than by somewhat shorter or longer distances. This is called the Baryon Acoustic Oscillation Scale, BAO. It's a subtle statistical feature in the galaxy distribution, a very slight excess of galaxy pairs at a specific separation. And because the physical scale is set by early universe physics that is very well understood, you can use it as a standard ruler. You know how large the BAO feature should be in physical units. You measure how large it appears in the sky as an angular size or a redshift separation, and the comparison tells you the expansion history, how much the universe has expanded between then and now, and how that expansion rate varied with time. DSI measures BAO in three-dimensional galaxy maps. It measures them at different redshifts, different look-back times, building up a record of how the expansion rate varied through cosmic history. Dark energy leaves its fingerprint in that record. A cosmological constant produces a specific pattern. Dynamical dark energy produces a different pattern. Phantom energy produces another. With enough galaxies measured precisely enough, DESI can distinguish between them. The 2024 DESI data release, based on 1 year of observations with about 6 million galaxy and quasar spectra, was, as we discussed, intriguing but not conclusive. The full 5-year program will produce around 35 million spectra. The statistical constraining power will be roughly 5 times greater. If the hint of dynamical dark energy in the year 1 data is a real signal rather than a fluctuation, it will be unmistakable in the full dataset. DC is not alone. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is conducting a complementary survey from orbit. Euclid's primary mission is to map the shape and distribution of galaxies across a third of the sky, using 2 complementary probes. The first is weak gravitational lensing, the VAR, subtle distortion of galaxy shapes caused by the gravitational effect of foreground matter. Measuring those distortions statistically maps the distribution of all matter, including dark matter, and reveals how that distribution has evolved with time. The second is galaxy clustering and BAO, similar to DESI, but from space, with different systematics and a different survey geometry. Euclid can see 2 billion galaxies across 10 billion years of cosmic history. Its combination of weak lensing and BAO provides 2 independent handles on the expansion history and the growth of structure, and the combination is far more powerful than either probe alone because they are affected differently by dark energy and by modifications to gravity. The Rubin Observatory, the Vera C. Rubin Observatory, nearing completion in Chile, will conduct the Legacy Survey of Space and Time, or LSST. Over 10 years, it will image the southern sky repeatedly, building a catalog of tens of billions of objects and detecting millions of transients, including, critically, tens of thousands of Type 1 supernovae, the same kind of exploding stars that revealed the accelerating expansion in 1998, but in numbers 100 times greater than anything previously assembled. Those supernovae will extend the distance ladder to higher redshifts than ever before and measure the expansion history with a statistical precision that makes the 1998 discovery look like a pilot study. The Nancy Grace Roman Space Telescope, NASA's next flagship mission after Webb, has a wide-field infrared camera designed in part for dark energy science. It will conduct a high-latitude wide-area survey covering 2,000 square degrees, combining weak lensing, galaxy clustering, and supernovae. Its infrared sensitivity means it can see Type 1 supernovae at higher redshifts than optical surveys, reaching back further in cosmic history, constraining the expansion history at epochs when dark energy was still relatively subdominant to matter and the signal of its evolution is most diagnostic. These 4 instruments, DESI, Euclid, Rubin, and Roman, constitute the dark energy observational program of the 2020s and 2030s. They were designed, collectively, to measure the dark energy equation of state, W, with a precision of a few %, and to measure its evolution, WLT, at a level that would detect a departure from the cosmological constant if one exists at the level current theoretical models consider interesting. By the early 2000s and 30s, their combined datasets will either have confirmed that W equals -1, the cosmological constant, stable, not going anywhere, or they will have found a deviation, a number slightly above -1, pointing toward quintessence, a number slightly below -1, pointing toward phantom energy, or a time variation suggesting dark energy is a dynamical field whose behavior may be unpredictable, If W comes back definitively below -1, if the data converges on phantom energy, the implication is stark. The universe's fate is not a heat death. It is a big rip. And the 22 billion year estimate, or something close to it, becomes not a speculative worst case, but an observationally constrained timeline. That timeline deserves to be examined in real detail, because most descriptions of the Big Rip treat it as an event, a moment when everything is destroyed. But the Big Rip is not a moment. It is a process, a long, ordered, systematic dismantling of the universe from its largest structures to its smallest, playing out over billions of years, with a physics that can be traced step by step. Let's trace it. Chapter 7. Inside the Big Rip. A billion-year countdown. The Big Rip has a specific mathematical structure. It is not a random catastrophe. It is the inevitable consequence of phantom energy's behavior applied to every gravitationally or electromagnetically bound system in the universe, from the largest to the smallest. The key is the scale factor. In cosmology, the scale factor, written as A of t, describes the relative size of the universe at time t. When the scale factor is 1, the universe is at its current size. When the scale factor is 2, the universe has doubled in linear extent 8 times the current volume. In a Big Rip universe with phantom dark energy, the scale factor does not grow gently and indefinitely. It grows to infinity in finite time. The rate of growth diverges. Space expands without limit, heading toward an infinite expansion rate, the singularity, within a calculable number of years. For the standard Big Rip calculation, which assumes a dark energy equation of state of W equals -1.5, consistent with the pessimistic end of observational uncertainties, that singularity arrives approximately 22 billion years from now. Different values of W give different timescales. W equals -1.1 gives a rip perhaps hundreds of billions of years away. W equals -2 brings it in closer to 10 billion years. W equals -1.5 is a commonly used benchmark, steep enough to be physically interesting, moderate enough to be within the range that current data cannot definitively exclude. Let's build the count down from that benchmark, from now to the end. 22 billion years before the end, now. The universe today looks the way it does. Galaxies clustered in groups and clusters, bound by gravity. The local group, our Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller companions, is gravitationally bound. Andromeda and the Milky Way will merge in about 4 billion years. The merged galaxy, Milkomeda, will remain bound through the entire period leading up to the final billion years before the rip. A few billion years from now, galaxy clusters begin to feel the strain. The expansion is currently accelerating, but it is not yet strong enough to overcome the gravity binding nearby galaxies into groups. But as phantom energy grows, the effective repulsive force at cosmological scales increases. Distant galaxy clusters, already weakly bound, their member galaxies orbiting with low velocities relative to the escape speed, begin to lose their outermost members first. Galaxies at the fringes of clusters find that the force pulling them back into the cluster is slightly insufficient to prevent them drifting away. Over millions of years, they spiral outward, lost to the expanding void. Roughly 2 billion years before the end, the Virgo supercluster dissolves. The Virgo supercluster, the larger structure containing our local group, The Virgo cluster, and dozens of other groups spanning about 110 million light-years, loses its gravitational coherence. The expansion, now significantly enhanced by phantom energy's growth, overcomes the weak gravitational threads holding the supercluster together. What had been a single large-scale structure fragments into isolated islands, each drifting away from the others. This is not an explosion. There are no fireballs, no shockwaves. From inside any of the separating galaxy groups, you might not immediately notice anything unusual. The sky within your local group looks much as before. But the distant clusters that once occupied specific positions in the sky, mapped by astronomers over generations, begin to drift in unexpected directions, receding faster than the standard cosmological model would predict. The large-scale structure of the universe is coming apart. Roughly 1 billion years before the end, galaxy clusters fully disrupt. Individual galaxy clusters, structures bound by the gravity of hundreds or thousands of galaxies, plus enormous dark matter halos, maintained over billions of years, are torn apart. The Virgo cluster, which at its center has the giant elliptical galaxy M87 and the supermassive black hole that was famously imaged in 2019, disperses. Its member galaxies, liberated from the cluster's gravitational embrace, scatter into the expanding void. For observers inside any of these galaxies, the sky is getting emptier. Galaxies that were once nearby, cluster companions, visible to optical telescopes, have now receded beyond observational reach, not just beyond the current horizon, but truly, permanently gone. The universe appears to be not just large, but suddenly, recently, noticeably more empty than before. Roughly 60 million years before the end, the Milky Way's outer structure begins to dissolve. This is the moment when the Big Rip stops being a distant cosmological abstraction and becomes something personal. The Milky Way, or Milkomeda, the merged galaxy that will have replaced it by this point, is a gravitationally bound structure spanning about 200,000 light-years, containing hundreds of billions of stars in a disk, bulge, and halo, held together by its collective gravity and its dark matter halo. For the vast majority of cosmic history, the expansion of the universe has been entirely irrelevant to the galaxy's internal structure. At 60 million years before the end, that changes. The phantom energy has grown powerful enough that its repulsive effect at galactic scales is no longer negligible. Stars in the outermost halo, the most loosely bound, orbiting the galactic center at enormous distances with low velocities, begin to experience a net outward push. Their orbits become unbound. They spiral away from the galaxy, lost to the expanding space around them. The process accelerates. The galaxy loses its outer halo, then its inner halo. The disk, the flat, star-rich structure containing the sun, the spiral arms, the gas and dust clouds, begins to fray at the edges. Stars near the edge of the disk find their orbits widening, their orbital periods lengthening, their connection to the galactic structure weakening. For any civilization still existing in Milkomeda at this point, the sky is changing in ways that can no longer be explained by normal galactic dynamics. Stars that should be in stable orbits are drifting outward. The edge of the galaxy, viewed in telescopes, is dissolving like salt in water. Roughly 3 months before the end, the solar system is torn apart. The pace of events has accelerated enormously. In the final year before the singularity, the expansion rate is growing rapidly. Structures that were safely bound are becoming unbound on timescales of months, then weeks, then days. 3 months before the end, the phantom energy's repulsive effect reaches a critical threshold within the solar system. The sun's gravitational pull on the planets, which has maintained planetary orbits to a precision of meters over billions of years, is suddenly insufficient. The expansion of space within the solar system, previously so negligible as to be unmeasurable, has grown to a significant fraction of the gravitational binding force. The outermost planets, Neptune, Uranus, lose their orbits first. They begin to drift away from the sun, moving, not in the hyperbolic trajectories of an object that has exceeded escape velocity through a boost, but in the more eerie fashion of an object whose orbit simply stops closing, whose gravitational connection to the sun is severed by the growth of space itself. The inner planets follow in sequence: Mars, Earth, Venus, Mercury. Each in turn finds its orbital velocity insufficient to maintain a closed orbit in expanding space. Earth drifts away from the sun. The distance grows. The solar flux reaching Earth's surface decreases. The planet, already uninhabitable for other reasons by this point, cools in the growing dark. Roughly 30 minutes before the end, the Earth disintegrates. In the final hour, the expansion rate is so extreme that structures bound by electromagnetic forces, solid and liquid matter, molecules, the chemical bonds holding rock and metal and water together, can no longer maintain themselves. The Earth, which has held together for over 14 billion years, maintained by the electromagnetic interactions among its atoms, begins to come apart. Not catastrophically, in the way a bomb destroys a building, more like the way a solid dissolves in a powerful solvent. The binding forces that hold everything together lose their contest with expansion, and the structure relaxes, spreads, disperses. The rock that forms the Earth's crust, silicates and carbonates and metals, bound by electromagnetic attraction between charged ions, separates into individual atoms. The liquid iron and nickel of the Earth's core, held together by metallic bonding, disperses into a cloud of individual atoms drifting in expanding space. Earth becomes a diffuse cloud of atoms spread across an enormous volume. An astronomical observer, watching from outside, might see it glow briefly as the energy of disruption is released, and then fade, the atoms too spread out to radiate efficiently. Final seconds, atoms dissolve, nuclei split, the singularity arrives. In the last moments, fractions of a second before the singularity, the expansion rate is so extreme that it overcomes the forces operating at subatomic scales. The electromagnetic force loses. Electrons in their atomic orbitals can no longer maintain stable configurations. The orbital radius, set by the balance between the electron's kinetic energy and the electromagnetic attraction of the nucleus, is disrupted by the expansion of space within the atom itself. Electrons are stripped from their nuclei. The atoms that have existed since the universe was 3 minutes old are ionized for the last time. Then the strong nuclear force loses. The protons and neutrons in atomic nuclei, held together by the residual strong force with binding energies of millions of electron volts, find that the expansion of space within the nucleus exceeds the range at which the strong force operates. The binding that has held nuclei together for 13 billion years fails in an instant. Protons and neutrons separate. And in the final instance before the singularity, if the standard model of particle physics holds to that point, even the protons and neutrons themselves may come apart. The quarks that compose them, held by the strong force at distances of roughly 10 to the minus 15 meters, but even that distance grows as space expands at an infinite rate. Then nothing, the singularity, an infinite expansion rate, the mathematical end of the solution. General relativity predicts it, but cannot describe what lies beyond it. The universe, in the technical sense, ceases to have a description accessible to current physics. This is the Big Rip. Not a single event, but a cascade. A systematic destruction of structure from the largest scale to the smallest, driven by the inexorable growth of a dark energy whose strength increases as the universe expands, until even the most tightly bound objects in nature cannot resist. It is, by any measure, the most violent and complete possible ending for the universe. And whether it will happen depends on a number, W, the dark energy equation of state, that we do not yet know with sufficient precision to decide. Chapter 8. What the data actually prefers, and the other possible futures. Let's come back from the abyss and talk about what the measurements actually show. Because the Big Rip, dramatic as it is not the most likely future the data currently points to. It is the worst-case end of the observational uncertainty. Understanding where the data sits and what other futures it is consistent with is essential for an honest picture. The dark energy equation of state parameter W has been measured by every major cosmological dataset for the past 2 decades. The CMB, combined with large-scale structure and supernova data, constrains W to be consistent with -1, the cosmological constant, to within roughly 5 to 10%. The central value in most combined analyses sits at W equals -1, or very close to it. No dataset taken alone has conclusively demonstrated W not equal to -1 at 5 sigma or above. The DESI Year 1 result, the 2 to 3 sigma hint of dynamical dark energy, is the most prominent recent suggestion that W might not be exactly -1. But it is a hint, and hints in cosmology have a poor historical record of survival. Cosmology is full of 2 sigma and 3 sigma anomalies that became more significant as more data came in, and full of others that quietly evaporated. The Hubble tension is an example of an anomaly that has grown stronger. There are also counterexamples where initial hints dissolved with better data. The most intellectually honest thing to say about the current state of dark energy measurement is this: the data is consistent with the cosmological constant, and there are suggestions, not yet conclusive, that dark energy might be evolving. The question of whether the universe ends in a big rip, a heat death, or something in between is genuinely open. Let's lay out the full menu of futures, ranked roughly from most to least favored by current data. The heat death, the cosmological constant scenario. If W equals -1 exactly, and remains there forever, the universe expands forever at an accelerating rate. Galaxies outside the local group recede beyond the event horizon over the next few 100 billion years. The Milky Way, merged with Andromeda into Milkomeda, burns through its remaining gas over the next few trillion years as the last stars form. The last red dwarf stars, the most efficient hydrogen burners in the universe, flicker out roughly 10 trillion years from now. the universe enters the degenerate era, a vast, dark expanse populated only by stellar remnants, white dwarfs slowly cooling, neutron stars spinning down, black holes growing slightly by occasionally absorbing stray matter. White dwarfs cool over tens of trillions of years, eventually becoming black dwarfs, cold, inert lumps of crystallized carbon and oxygen radiating nothing, orbiting each other and the occasional black hole in the dark. Over incomprehensible timescales, 10 to the 40 years or so, protons may decay. If grand unified theories are correct and protons have a finite lifetime, every piece of ordinary matter in the universe eventually dissolves into a diffuse cloud of electrons, positrons, and photons. The white dwarfs and neutron stars, which had seemed like the most permanent structures in the post-stellar universe, slowly evaporate. Black holes outlast everything. They can only lose mass through Hawking radiation, the extraordinarily slow quantum process by which a black hole radiates energy as if it were a thermal body at a minuscule temperature. Stellar mass black holes evaporate after about 10 to the 67 years. Supermassive black holes, the billion solar mass monsters at the centers of galaxies, take up to 10 to the 100 years. A Google years. After that, the last Hawking radiation flash fades, and the universe is left with an essentially empty, expanding void, populated only by the occasional stray photon and a thin background of electrons and positrons at temperatures indistinguishable from absolute zero. This is the heat death, thermodynamic equilibrium, maximum entropy, the state from which no useful work can ever be extracted. By the standards of human experience, it is a horror, an eternity of increasing emptiness, with no warmth, no light, no events. But it is a horror on timescales so vast that every moment of cosmic history up to this point, including the entire future lifetime of the sun, is a rounding error. If this is the fate of the universe, it is at least a comprehensible fate. Not violent, not sudden, just a slow, patient slide toward nothing. Quintessence, the slow fade. If W is greater than -1, if dark energy is a field that weakens slightly over time, rather than staying constant, the future is broadly similar to the heat death, but with a subtly different character. The acceleration is still happening now, but it is gradually weakening. Over cosmic time, as the dark energy field rolls down to lower values, the expansion rate may slow. In some quintessence models, the field eventually reaches zero. Dark energy disappears entirely, and the universe's future expansion is governed by the residual matter and radiation, which produce a gently decelerating expansion rather than an accelerating one. In these models, the distant future is even more like the classical heat death, a universe expanding, but not accelerating, with galaxies more slowly separating and the cosmic web maintaining a slightly less dramatic isolation. The ultimate fate is still maximum entropy, but the timeline may be longer and the intermediate universe slightly less lonely. Quintessence is a class of theories, not a single model. Different versions make different predictions for how quickly dark energy evolves and what value it settles to. Some versions allow for dark energy to oscillate, growing, shrinking, cycling, which would produce a complex expansion history that no current measurement hints at but cannot entirely rule out. The Big Crunch, the collapsed future. If dark energy is not constant but evolving, and if it evolves in the direction of becoming negative, a repulsive force that turns attractive. The expansion could slow, stop, and reverse. The universe would begin contracting. Galaxies would approach each other. The CMB would blue shift, getting hotter rather than cooler. The night sky would gradually brighten as blue-shifted CMB photons carried more energy. Galaxies would merge. The cosmic web would collapse. Eventually, everything would converge on a final singularity. A hot, dense endpoint that mirrors the Big Bang, but in reverse. The Big Crunch is deeply unfavored by current data. The expansion is not slowing. It is accelerating. For a Big Crunch to occur, dark energy would have to reverse sign at some point in the future, something no current measurement supports, and which would require a radical revision of our understanding of dark energy's behavior. But it is a logically possible future, entertained in some theoretical models, and honest accounting of the possibilities requires including it. The Big Rip, the violent end. You know this one. W below -1, phantom energy. The scale factor diverging to infinity in finite time. The systematic destruction of every bound structure in the universe, from galaxy clusters to atoms, in the 22 billion year countdown. It requires a specific value of W below -1 that current data does not require but does not rule out. Its probability, given the current observational constraints, is not 0. The false vacuum, the silent end. There is a fifth possible fate that operates on its own timescale and does not fit neatly into the dark energy taxonomy. We touched on it in Part 1, Vacuum Decay. If the current vacuum state of the universe, the ground state of the Higgs field, and the other fundamental fields, is a false vacuum rather than the true vacuum, then a quantum tunneling event anywhere in the universe at any time could nucleate a bubble of lower energy vacuum that expands at the speed of light. This bubble, as discussed, would carry different physical constants and make complex chemistry and life impossible. It would be invisible until it arrived. No warning, no precursor, just the instant conversion of everything inside it to a universe with different physics. The timescale for vacuum decay, given current best estimates of the Higgs boson mass and the top quark mass, is extraordinarily long, probably much longer than the heat death timescale, on the order of 10 to the 100 years or more. But it is not infinite. And unlike the heat death or the Big Rip, it does not depend on dark energy at all. It is a possibility that exists regardless of the dark energy equation of state, operating silently in the background of whatever cosmological future dark energy produces. The most sobering aspect of vacuum decay as a potential fate is its completeness. In the Big Rip, the destruction takes billions of years and operates systematically. In the heat death, things exist for unimaginably long times, just at lower and lower energy. In vacuum decay, there is no process, there is no warning, there is no sequence of events leading up to it that allows for observation or adaptation. There is just the present moment, and then the bubble arrives, and then a universe with different rules where nothing we know can exist. It may already be on its way. Somewhere in the universe, right now, in a galaxy we have never observed and could not observe, a bubble of true vacuum might have nucleated, moving at the speed of light, getting closer second by second. We would never know until the moment of arrival, which would be indistinguishable from the moment of non-existence. Most physicists think this is unlikely to happen anytime soon, given the estimated lifetime of the false vacuum. But unlikely soon is not impossible, and it represents a reminder that the future of the universe is not entirely under the control of dark energy. Chapter 9. What it means that we don't know here is where I want to step back from the physics for a moment and say something about what this whole situation means, about what it means to live in a universe where 68% of its energy content is something we don't understand, driving a process we've only known about for a quarter century, with consequences ranging from a long cold darkness to the complete destruction of all matter in 22 billion years. We tend, in science communication, to present the unknown as a gap, a space between things we know, which will eventually be filled by more knowledge. And in many areas of science, that's right. We don't know exactly how life on Earth began, but we have a good framework and specific testable hypotheses. We don't know the mass of dark matter particles, but we have candidate masses and ongoing experiments to find them. Dark energy feels different, not just unknown, but fundamentally, philosophically, almost offensively unknown. It is the dominant component of the universe, and we do not have a single confirmed theoretical prediction for what it is or where it comes from. The best theoretical idea we have, vacuum energy from quantum fields, predicts the wrong answer by 120 orders of magnitude, a discrepancy so enormous that it suggests we are missing not a small correction, but an entire principle of physics. Something we have never considered, or perhaps something we have considered and dismissed for the wrong reasons. There is a way of thinking about this that I find genuinely humbling. Before 1998, cosmologists thought they understood the broad strokes of the universe's composition, matter and radiation governed by gravity, expanding from the Big Bang. Simple, elegant, fitting all the available data. And then two teams of astronomers looked at some exploding stars and found that the universe had, all along, been dominated by something none of them had included in their models. Something that had been hiding in plain sight, or rather, hiding in the emptiness between galaxies, exerting a force that was larger than the combined contribution of all matter and radiation, and that nobody had detected because it doesn't cluster and doesn't emit light and doesn't interact with anything we measure directly. In one sense, the discovery of dark energy is a triumph. We found it, even though it had no properties we could observe directly. We inferred it from its effect on the cosmic expansion history, and the inference was correct, confirmed by multiple independent methods. In another sense, the discovery of dark energy should make us fundamentally humble about what else might be out there that we haven't detected yet. If 68% of the energy content of the universe went completely undetected for the entire history of observational astronomy until 1998, what else are we missing? What other dominant component might be operating in ways that none of our current instruments can see? The honest answer is, we don't know. And we don't know what we don't know. And the history of dark energy suggests that what we don't know can be bigger by energy content than everything we do know. The cosmological constant problem makes this unease more acute, not less. It's one thing to say we haven't yet explained dark energy's value. It's another to say that our best theoretical framework, quantum field theory, the most precisely tested theory in the history of physics, gives a prediction that is 120 orders of magnitude wrong. That isn't a small systematic error in a calculation. That is a catastrophic failure of a theory in a regime where we have every reason to expect it to work. The only conclusion that is consistent with both the theoretical failure and the observed value is that something, some cancellation mechanism, some symmetry principle, some aspect of quantum gravity or string theory, or an entirely undiscovered framework, is suppressing the vacuum energy by precisely the right amount to leave only the tiny residual we observe. That suppression has to be accurate to 120 decimal places. It has to cancel the enormous quantum contributions and leave a remainder so small that it only dominates the universe's dynamics on cosmological scales. This is called the fine-tuning problem of the cosmological constant. And it is genuinely troubling, not in the casual way that physicists describe many unsolved problems as interesting challenges, but in the deeper way of a problem that suggests the foundations of our theoretical understanding are missing something essential. Some physicists believe the answer lies in the multiverse, that in a landscape of many possible vacuum states, most universes have enormous cosmological constants and are lifeless. And we find ourselves in one with a small cosmological constant simply because that's the only kind of universe where observers can exist to notice. This is the anthropic reasoning applied to dark energy, and it has some mathematical support from string theory's landscape of vacua. It is also, by the usual standards of physics, deeply unsatisfying. It predicts nothing beyond the observation it's invoked to explain, and it may be permanently untestable. Others believe there is a genuine physical mechanism, a dynamical field, a symmetry, a quantum gravity effect, that will eventually explain why the cosmological constant has the value it does. That the fine-tuning is not a brute fact, but a consequence of physics we haven't yet discovered. This is a more optimistic view, and the history of physics, where apparent fine-tuning problems have often been resolved by the discovery of new principles, gives some reason for it. Either way, dark energy sits at the intersection of the two great unresolved problems in fundamental physics: the failure of quantum field theory to predict the vacuum energy, and the absence of a theory of quantum gravity that could make sense of the large-scale structure of space-time. Whatever dark energy is, understanding it will require resolving at least one of those problems. It is not a question at the periphery of physics. It is a question at the very center. There is something else worth saying about the 22 billion year Big Rip timeline. Even in the worst case, even if phantom energy is real, even if the Big Rip is coming, 22 billion years is a period of time almost incomprehensible in human terms. The universe is currently 13.8 billion years old. The Big Rip, if it comes, arrives in 1.5 universe lifetimes from now. The sun will have burned out about 5 billion years from now. The last red dwarf star will burn out in several trillion years if dark energy doesn't intervene. We are talking about a future so distant that every piece of history, every civilization, every star, every geological epoch that has ever occurred is a tiny fraction of the remaining time. In that time, if intelligent beings persist, which is itself a deep question, the problem of dark energy will not remain unsolved. The instruments of the 2020s and 2030s will constrain W to percent level precision. If phantom energy is operating, its signal will be detectable in the data within years. If the Hubble tension is resolved by new physics, that new physics will be identified and tested and refined over centuries. If string theory or some successor produces a principled prediction for the vacuum energy, that prediction will be tested against observations over millennia. The unusual thing happening to the universe right now, the accelerating expansion, the mysterious dark energy, the possibility of a violent end, is not a fixed fate handed down by inscrutable physics. It is a description of the current state of our knowledge and the current state of the universe as we understand it. Both of those things change, rapidly by astronomical standards. We will not go to our end if an end is coming in ignorance. The beings who inhabit the universe in 1 billion years, if there are any, will understand dark energy with a clarity and completeness that we cannot imagine. They will have had 1 billion years of additional observations, 1 billion years of theoretical development, 1 billion years of accumulating exactly the kind of precision data that DC and Euclid and Roman are just beginning to collect. Conclusion: the most important number in the universe. Let me bring you back to now. Right now, as you watch this, the universe is expanding. The space between the Milky Way and the Virgo cluster is growing by about 1,100 kilometers every second. The fabric of space-time is stretching, driven by an energy that permeates every cubic meter of empty space and that we do not understand. The expansion is accelerating, has been accelerating for about 5 billion years since dark energy overcame the decelerating effect of matter and took control of the cosmic dynamics. Right now, DESI is operating at Kitt Peak. Somewhere in the Arizona sky, 5,000 robotic fibers are repointing themselves, settling onto a new field of galaxies, beginning to measure 5,000 new redshifts that will add 5,000 new data points to the map of the expanding universe. Euclid is somewhere between the Earth and the L2 point, its wide-field camera accumulating light from billions of galaxies, measuring their shapes with the precision needed to detect weak gravitational lensing at the percent level. Rubin's dome is open in Chile, its 3.2 gigapixel camera sweeping the southern sky, looking for transients, looking, among other things, for the next Type 1a supernova that will add one more data point to the most important distance ladder ever built. All of these instruments are converging on the same number. W, the dark energy equation of state, the number that determines whether dark energy is the cosmological constant, stable, constant, leading to a quiet, frozen end, or something dynamic, something changing, something that could eventually grow strong enough to tear the universe apart. That number is currently constrained to within about 5 to 10% of -1. The constraint will be 10 times tighter by the time DC, Euclid, Rubin, and Roman complete their programs in the early 2030s. If phantom energy, W below -1, is real, it will be detectable at high significance with that data. If it is not real, the measurements will confirm the cosmological constant with a precision that leaves no room for doubt. In less than a decade, we will know whether the Big Rip is coming, not with certainty. Physics never offers certainty. It offers probabilities, constraints, confidence levels. But with enough precision to say, with confidence, whether the universe's future is a long, cold quiet or something far more dramatic. The most unusual thing about what is happening to the universe right now is not the expansion. It is not even the acceleration. It is this. We live at the precise moment in cosmic history when the technology exists to measure the expansion's ultimate fate, and when the instruments are being built to do exactly that, and when the data is coming in. For the entire 13.8 billion year history of the universe before this decade, the question of whether W equals -1 or -1.1 or -0.9 was completely inaccessible to observation. The universe has been expanding and accelerating for 5 billion years, and for the first 4.8 billion of those years, no instrument existed that could have detected it. We have had the ability to observe the accelerating expansion for 25 years. We have had the ability to measure dark energy's equation of state at the level of percent for less than a decade. We are the first generation of observers in the history of the universe capable of asking and beginning to answer the question of what dark energy is and what it will do. This is the unusual thing happening right now to the universe. Not just the physics. The fact that the physics is being measured right now, for the first time, by the first species in the history of the cosmos to build instruments capable of detecting it. We are not passive observers of the universe's fate. We are the universe's attempt to understand its own fate. And the attempt is going well. Think about what it means that the answer to the question, how does the universe end, comes down to a single number that a spectrograph in Arizona is measuring right now, one galaxy redshift at a time. That the entire arc of cosmic history, from the Big Bang to the last photon, is encoded in a parameter describing the ratio of pressure to energy density in the vacuum of space. That the difference between W equals -0.99 and W equals -1.01 is the difference between a universe that ends in frozen silence and a universe that ends in the complete destruction of all matter, and that the measurement distinguishing those two futures requires observing millions of galaxies spread across billions of light years, and comparing the statistical imprint of acoustic oscillations in the early universe with the observed distribution of matter today, and doing all of that at a precision of a few percent. The chain from the question to the answer is extraordinary in its length and in its fragility. Every link in that chain, the theoretical framework connecting W to observable signatures, the engineering required to build the spectrograph, the algorithms required to process millions of spectra, the calibrations required to remove systematic errors, represents decades of accumulated scientific and technological effort. The ability to ask the question at all, let alone answer it, is one of the most complex achievements in the history of the species. And the people doing it are not doing it because they are afraid of the Big Rip. They are doing it because the question is real and answerable, and because the answer will tell us something about the structure of reality that nothing else can. Whether or not the universe rips apart in 22 billion years matters less, in practical terms, than whether 1,000 specific policy decisions get made correctly in the next 10 years. But it matters enormously in the other sense, the sense in which understanding the nature of the universe we inhabit is its own reward. The number is coming. in this decade or the next. And when it comes back, it will be the most important number ever measured.